In this show, they're going to take us to a water plant. Then they're going to show us how electronic fuel injection works. First, here's how batteries work. I don't use batteries. I have a spring.
This week on Acme School, batteries. Well, gosh. Strictly speaking, these things aren't really batteries. They're cells. This is a battery. It's a 9-volt battery. Inside is a battery of cells. Each cell in the 9-volt battery is 1.5 volts. And the 9-volt battery has a stack of 6 1.5-volt cells. The voltage of a cell is a matter of the irrevocable laws of the universe. It doesn't depend on its size. If you scaled one of these up till it was the size of a house, it would still deliver 1.5 volts. But it would last for a very long time. The voltage is important to the design of a battery-operated device, and the designers will design a unit to operate on 1.5, 3, 4.5, 6 volts, and so on. That's 1, 2, 3, 4, 5 cells, and so on. The amount of power that the unit uses determines the physical size of the cells. A 90-watt boogie box will operate on the tiny AAA cells for a minute or so. Now, cells have been around for about 200 years, and they all have similar components. That is, 2 electrodes of different metals in connection with an electrolyte. I submit to you a brass bathtub and a magnesium rod, the electrodes, and, nothing up my sleeve, salt water, the electrolyte. No one is more amazed than I am when this works. As we say in the science business, ta-da! In case you think I'm getting something for nothing, the energy that's coming from this cell is the energy that was put into the magnesium when it was refined from ore. In other words, this cell works by corroding the magnesium. Cells that used a wet electrolyte like that salt water were the first cells discovered. The most common use today of wet cells is the car battery. Wet cells aren't really too portable. Now, it was possible to make a cell with a paste electrolyte, but since cells work by corroding one of the metals, early dry cells would go dead while they were on the shelf waiting to be used. It was 1888 before the chemistry came along that could give the cell a good shelf life. And that cell would not destroy itself while it was waiting. It was ever ready, so to speak. It occurred to someone that was a pretty good name for the cell. I guess you know the rest. This is the classic carbon cell. Ask me why it's called a carbon cell.
Why is it called a carbon cell? Why is it called a carbon cell?
I don't know. It has a carbon rod in the center, but it's not part of the reaction. The electrodes in a carbon cell are the zinc can that holds everything, and manganese dioxide. The electrolyte is a mixture of ammonium chloride and zinc chloride. It's hard to point all that out because the electrolyte is all mixed in with the manganese dioxide. There's a separating layer of flour and starch near the zinc can if you want the full recipe. The carbon rod runs down the center just as a convenient method of making connection to the paste. It's interesting to note about the carbon cell that it works by corroding its own container. And because plain zinc is the metal that's used, the electrolyte needs to be aggressive, so it's slightly acidic. It's also interesting that if this were a pocket watch, it wouldn't work after I cut it in half, but there's a difference between pocket watches and basic chemistry. You may have seen the mess that an exhausted carbon cell can make. These cells are designed not to leak. Instead, they're designed to die before they corrode their own container all the way through. There is one way to get them to leak, though. Put a dead one in the company of fresh ones. The new ones will force current to flow through the dead one long after it should. That's why cells should always be replaced in sets. The carbon battery is cheap and performs well. Here's a personality profile. Being cold improves its shelf life, which is 1 to 2 years, but it won't work when it's cold. Forget it for emergency car flashlights. It's cheap. I use them in battery-operated radios because it doesn't cost much when you forget to turn them off. It begins to die as soon as you start to use it. It goes out on a long, graceful curve, so it won't die without warning, but it's not great for applications that are demanding. It's still my favorite general-purpose cell, because of the price. This is the heavy-duty version of the carbon cell. Fancier chemistry, more money, and a slightly different personality. They deliver higher currents longer than the regular zinc carbon cell, and by a nice quirk, the electrolyte gets drier as the cell gets exhausted, lessening the chance of leakage. Heavy-duty carbon cells can be thought of as improved carbon cells. Here's the one you were waiting for, I bet. Alkaline. These cells are radically different from carbon cells, as I found when I sawed one of them in half. The basic dead end in carbon cells is that pesky zinc electrode that has to function as a container. The alkaline cell uses a steel can that isn't involved in the reaction. The electrodes and electrolyte can all be optimized for performance then, and they're powdered and compressed into the can. Compared to the good old carbon cell, the alkaline's upside down in its container. A metal nail makes connection to the paste and it's connected to the bottom of the cell. Now, partly because of the efficient chemistry, the electrolyte doesn't have to be acidic. It's alkaline. This cell is more costly to manufacture and they pass that on to you. In a lot of applications though, they're well worth the price. Facts and figures. They'll deliver a heck of a lot of current if they have to. They last longer than any other cells. They have the best shelf life and they work in the cold. They perform well throughout their entire life rather than the slow decline of carbon cells. And they're a must for any serious device, like a flash unit. Nickel cadmium, NiCads. They have something special about them that the others don't. The chemical reaction in them is reversible. When they're exhausted, a current can be forced backwards in them to recharge them. They can also deliver the most current of any cell that you or I can buy. And that's all I have nice to say about them. The bad news. They have a shelf life of a couple of months. They're dead when you buy them. That should tell you something. Their cell voltage is not 1.5 like all the others. It's 1.2. You'll find that things designed to use ordinary cells will have slightly reduced performance. They have a memory. If you use them lightly and recharge them often, that's the way they'll start behaving. You have to run them low as often as you can. They die suddenly with very little warning, 30 seconds or so. Don't ever use them in a smoke detector. They take about 10 times longer to charge than to drain. It's not all bad news for NiCads though. Things that were designed for them work well. There's a whole range of battery-operated stuff that wouldn't even exist if it weren't for nickel cadmium's rechargeability. Okay. Ask me what's in the button cells.
What's in the button cells?
Everything and anything. Button cells are made with all different chemistries for a lot of different applications. They go by the names of silver, lithium, mercury, alkaline, and air cells. That's why there's such a different array of diameters and thicknesses. That's also why you can never find the ones that fit right. I think I finally got the problem beat though. I've calculated this D cell should last about 500 years. Let this tap flow for a while and you'll have a lot of water. Let it flow for a day and you'll have a real lot of water. Multiply that by a couple of million households and you'll have a whole real lot of water. This is Lake Ontario. It too is a whole real lot of water. The main difference between Lake Ontario and Toronto tap water is that the lake is full of fish, boots, wood, algae, bacteria, and various other things that don't come out of a tap, thank goodness. This is the R.L. Clark Water Treatment Plant, one of 4 supplying metropolitan Toronto with its water supply. Preparing raw lake water for drinking is more complicated than just dropping in a little chlorine pill on a camping trip. The chemical and bacterial content changes with the time of day, season, and wind direction. This unassuming little meter shows the current flow out of the plant. It's a little over 6 cubic meters per second. Maybe your TV room is 6 cubic meters in size. That amount of water is monitored and treated here every second. 1,600 meters out and 18 meters deep is the water intake. That's almost a mile and real deep. A screen on the intake eliminates the boots and most fish. The incoming water is below in 30-foot deep wells. A continuously moving screen catches leaves and small fish that might make it this far. Those things are returned to the lake. Bye, little fishy. From the wells, it's pumped up to the 3rd floor of the plant using giant pumps and piping. If giant is a little too vague for you, I checked the rating plates on the electric motors. 350 horsepower each. Now that the water is free of fish, leaves, and boots, it's time to get to the more serious treatment, removal of suspended matter and bacteria. A handy way to help remove the tiny particles that make the water cloudy is to turn them into bigger particles. This is done by a process called flocculation. Alum is added. The alum causes small particles to flock together into larger clumps. The amount of alum is adjusted by monitoring how cloudy the incoming water is. The alum is added by paddle wheels in measured amounts. The name of this machine is the rotodip. In these tanks, the water is slowly stirred to encourage the clumps to form. These arms are moving wooden paddles slowly up and down. The clumps are mostly algae and suspended matter, but some bacteria is trapped here too. The next stop will be an underground settling pool where the heavier clumps fall to the bottom. Here's something I forgot to ask about. Here's something I didn't ask about. Fine material that didn't fall out in the settling tanks is captured right here. These are the filter beds. Starting up from the bottom of each pool are 18 inches of foundation aggregate, that's rocks to you and me, 12 inches of sand, and 18 inches of powdered anthracite. It's like charcoal. Water flows continuously in each filter, in at the top and out at the bottom, until the outflow indicates that the filter is getting clogged. Then comes a flush that really has to be seen in person. The incoming water is stopped and the water level in the filter slowly goes down. Then a torrent of water is released under the filter and forced backwards through the filter. This causes trapped material to flow out of the sand and anthracite back to the lake. The backflushing continues until the filter is clean. So much for suspended material, but what happens to all that bacteria? This is the on-site lab. Incoming and outgoing water are constantly monitored for anything nasty. Since the incoming water changes with a number of factors, including which way the wind is blowing, the lab and control room constantly adjust the purification process. This room controls the addition of various compounds that disinfect the water supply. To ensure good mixing, compounds are added as gases by these machines. Incoming water is heavily dosed with chlorine to zap algae, bacteria, and viruses. And after the nasties are dead, the leftover chlorine is brought back to acceptable levels by the addition of sulfur dioxide. Ordinarily, this small chlorine residual would disappear in a few hours, so ammonia is added in small amounts to fix the chlorine so that it'll last the trip through the miles and miles of pipes and reservoirs. Speaking of small amounts, this pipe is the flow of well, the name's on the pipe. It's the fluoridation for your teeth. This flow is the amount being added to 6 cubic meters per second of water. It's a genuine small amount. It's clean, it's clear, it tastes good. Maybe we could bottle it and sell it. It all started with a simple question. Why are car manufacturers moving to fuel injection on gas engines? See, fuel injection's been around on diesel engines for at least 100 years, because a diesel engine relies on a precisely timed squirt of fuel to operate. A gas engine relies on a supply of fuel and a precisely timed spark to function. Ever since the invention of the gasoline engine, a real simple device has been used to provide the fuel, a carburetor. Here's the basic idea behind carburation. A fast-moving stream of air passes a small nozzle, and the fast-moving stream of air creates a low pressure near the nozzle. That sucks the fuel out. Because the nozzle's small, the fuel enters the airstream as tiny droplets. By selecting the correct size nozzle, the mixture of air and fuel can be controlled. The exact mixture of air and fuel used to be merely important, but with the addition of catalytic converters for pollution control and new gas mileage regulations, the mixture of air and fuel has become extremely important. That mixture, if you care, is a ratio of 14.7 parts air to 1 part fuel. Now, because of the pistons going up and down in their cylinders in an engine and the action of the valves, the engine actually acts like a great big vacuum cleaner, sucking air in and blowing it out. It's that incoming stream of air that passes through the carburetor and have fuel added by the nozzle. The carburetor works effectively at highway cruising speeds, but in other situations it gets messy. During starting, the engine needs a little bit more fuel, so a plate's rotated to make the engine suck harder against the nozzle. This is the famous choke, and that's a good name for it. The choke releases when the engine warms up, usually. The other situation that requires more gas is acceleration. In actual fact, when you press the accelerator pedal, you rotate this disc, allowing the engine to suck more air-fuel mixture. Now, this alone won't speed up the engine. See, when the throttle plate's partially closed, the engine's sucking against a restriction. There's quite a bit of suction, or vacuum, in the intake pipes to the cylinders. When your foot opens the throttle plate, that vacuum level drops. A small hose connected to the ignition system uses that drop in vacuum to make the spark plugs spark a little earlier. Now, at that moment, the air passage is fully open, the spark timing is increased, and the engine will speed up gradually. See, until it sucks more air by speeding up, it won't suck more gas, and it needs more gas to run faster. The catch-22 eliminator is the accelerator pump. This little devil squirts an extra burst of fuel down the hole when you stomp on the gas pedal, giving the engine the fuel it needs to accelerate. The accelerator pump will also flood the engine with too much fuel when you stomp on the pedal repeatedly. That's the basic carburetor. It's just a nozzle to meter fuel. And everything else here is added to make up for situations when the engine isn't going down a flat highway at a constant speed. With the increased importance of maintaining a correct air-fuel mixture, it's getting just a little complicated and a little expensive. Let's start over. The engine's a big air pump, and all we have to do is squirt a mist of gas into it to keep it running. That's an injector. Liquid fuel is provided to it at a constant pressure. When an electric current's supplied, an electromagnet opens a valve and the fuel squirts out of a tiny hole. The injector is an on-off device. It either squirts or it doesn't. But by pulsing it on and off rapidly, the amount of fuel it squirts is adjustable. Here's one way to replace the good old carburetor. This unit goes on the air intake of the engine. Now there's still a throttle plate in the airstream controlled by your foot. This thing regulates the fuel pressure so that the only variable is the length of the squirt. The squirts are pulsed at under 1,000th of a second, so it appears as if the spray is constant. If you haven't already guessed, the injector is controlled by a computer. Had to happen, didn't it? But as long as we have to have a computer, we can give it all sorts of interesting inputs. Here's a little survey. This, located at the other end of this rod, is the throttle position sensor. Your foot still controls the throttle, but the computer knows what you're doing. This is information to and for the ignition system. This sensor measures the oxygen content in the exhaust gases. Here's the engine temperature sensor and the NOx sensor. Well, actually we don't have a NOx sensor here, but it's basically a microphone. There are more sensors monitoring just about every engine parameter you can imagine, and some cars will have more or less sensing, but it gives you the basic idea. The computer has 3 outputs. One goes to the ignition system to time the spark exactly. One goes to the fuel injector, pulsing it on and off rapidly to keep the air-fuel mixture right. And the other one goes to this thing. It's a small motor that allows the computer to fine-tune the airflow when your foot isn't on the pedal. See, the computer does more than just keep the fuel flowing at the right amount. For instance, if you turn on the air conditioner with the engine idling, it'll intercept that command, increase the idle speed a bit, then allow the air conditioner load to be added to the engine. If you hold the throttle all the way down while you're starting, it'll assume the engine's flooded and act accordingly. During warm-up, the computer knows to take some of its inputs with a grain of salt and to ignore the oxygen sensor entirely. It needs to be hot to work. If any of its inputs go defective, it'll light a warning light. It'll even describe the trouble to someone with the correct service tools. In the worst of cases, if it's unable to take command of everything, it'll set the gas flow to medium to let you drive it to the service shop. It's called the limp home mode. Now, because of where the injector is located on this layout, it's called throttle body injection. Since it replaces the carburetor directly, it and the computer and all the sensors are really just sort of a high-tech carburetor replacement. The throttle body unit still delivers gas and air down a fancy set of pipes to the individual cylinders. Tune port injection goes by several names. In this arrangement, each cylinder has got its own injector, and the opening and closing of valves to suck air causes the incoming air to pulse. It's a lot like playing the tuba. Now, each cylinder having its own injector allows the designer to optimize the intakes for the pulsing airflow, hence the name tune port. If you take tune port and add another computer wrinkle, you get sequential fuel injection. With sequential, each injector is fired only as its intake valve is about to open. It's a little more complex, but currently the high art of electronic fuel injection. So, computer and tons of sensors that would have been science fiction a few years ago. The result is better mileage and a non-polluting car that's fun to drive. The question was, why fuel injection? Why not?